Alright, welcome back. This is the third talk on Foundations of Mathematical Proof, and today I'm going to be introducing some logic, so it's going to be some more discrete stuff. We'll go over truth tables today and logical equivalences. So, first I want to start off with some definitions. So, a statement is a sentence which is either true or false. We will note statements with capital letters. An open sentence is a sentence with a variable, and putting different values into the variable creates statements over a domain set where the domain is where the variable comes from. Denote P of X, where P is the statement and X is the variable. So these might seem a little odd when you first look at them, but it's pretty simple. So 3 equals 5. That's a statement, because it's false, so it's either true or false. So even though 3 equals 5 is false, it's still a statement. P of X is what our open sentence is going to be, and it's going to be X is equal to 9. So P of X, it could be true or false, depending on what X is. When X is 9, P of X is true. But when X is not equal to 9, P of X is false. So statements are just there and they're either true or false. But open sentences, their truth value depends on some other variable. So that's the difference between a statement and open sentence. Alright, now I want to get into some more logic. So let P and Q be statements. So P and Q are either true or false. So P and Q is a new statement denoted P. It's an upside down VQ. It receives a truth value of true if both P and Q are true, and a truth value of false otherwise. So P and Q is true when P and Q are true. So if one is false or both are false, P and Q is false. P or Q is a new statement denoted P VQ. It receives a truth value of true if either P or Q or both are true, and a truth value of false if both are false. So at first, sometimes students get or confused because they think that only P is true or Q is true and both aren't true. If both, you can only have one be true but not both. But it's one or both are true. Think of it not like you're ordering at a restaurant and they're like, would you like fries or a salad, where you only can choose one. It's more like a buffet where you have fries or a salad, or you can have both fries and a salad. So, or one or both are true. If both are false, or is false. And last one is just the negation of P, which I like to note by the tilde and then P. It's a new statement which receives a truth value of true when P is false and a truth value of false when P is true. So basically, it just negates it. Pretty simple. And when you work with logical statements like this, it's sometimes easy when you first start to use a truth table. So a truth table, when we're just looking at it, we have P and Q, and then we have P and Q. So we see when P and Q are true, P and Q is true. Whenever one of them or both of them are false, P and Q is false. And you might want to try constructing these tables on your own to help you get more familiar with the logic behind everything. So the truth table for or, notice P or Q is true when both of them are true, P is just true, Q is just true, and so it's either one or both. And it only receives a value of false when both P and Q are false. In negation, it's pretty simple. P is true, not P is false. P is false, not P is true. So, logical equivalences. So this is where we get into the meat of logic. So let S and R be two compound statements using the same component statements. We say that S and R are logically equivalent if they receive the same truth values for all possible combinations of the truth values of their components. So basically, this is just a really long way of saying that you have two compound statements and they're equivalent when they have the same truth values no matter what their components are. So, and we'd note this, S is equivalent to R. And you can use truth tables to actually prove that these equivalencies hold, and that's what we're going to do in the next slide. So here's a proof. We're going to prove that P and Q, or P and not Q, is equivalent to P. So I set up the truth table here, and you see, since P was on the right hand side, and it was the shorter of the truth values, I just put it on the left. And notice I build up from P and Q the components, the big statement of P and Q, or P and not Q. And if you notice, in the first column and last column, no matter what P and Q are, the statement is the same. So we say that this statement up here is a logical equivalence. And now there's a couple logical equivalences that are really basic and you really need to know just off the back of your hand. And I'm not going to prove them, but it's a great exercise if you want to go and build the truth tables to prove that they are equivalent on your own. So we have P and Q is equivalent to Q. Oh, P or Q is equivalent to Q or P. Sorry, I mix up the ors and ands. A little trick is I like to kind of think of the V as a boat, and you use an or to row a boat, and the and it kind of looks like an N that points, so I think of the N and. So that's a neat trick. So next equivalence is P and Q is equivalent to Q and P. Next one is P or Q or R is equivalent to P or Q or R. Likewise, we have P and Q and R is equivalent to P and Q and R. Likewise, we have P or Q and R is equivalent to P and R or Q and R. And you might notice that these kinds of look like unions and intersections, and that's kind of where our equalities for unions and intersections came from, is we actually used these logical equivalences when we were proving how to open parentheses when we have both unions and intersections. And the last one's pretty obvious, but at the same time, you would have to prove that this holds, that not P is equivalent to P. Oh, I think there's one or two more. Not P or Q is equivalent to not P and not Q. And then not P and Q is equivalent to not P or not Q. And that is the end of this lesson on logical equivalences. Next time I'll pick up with implications, and then we'll move on to quantifiers, and that'll wrap up logic. Thanks for watching, and come back.